All right, folks, so in this lesson we are going to now look at quadratic functions. Now that we have an understanding of how to identify important characteristics of linear functions, we're now going to identify important characteristics of quadratic functions. Now, I want to point out that I have added two qualities that are unique to polynomial functions that are not linear. I have identified what's called a critical x and what's called a lead coefficient. The lead coefficient is actually a really simple concept. It's really easy to identify. I'll explain it when we get to it. But this critical x is also very easy to identify, but I want to talk about it for a second, how important it is. A critical x is an x value at which, for a particular function, the output values basically change direction. So let's say that I had just a list of values, x and y, and let's say at a value of, if I plug in 7, let's say I get 19. And then if I plug in 8, I get 32. And if I plug in 9, I get, let's say, 38. But then when I plug in 10, notice what's happening here with the y values. They're going up, right? We have an interval of increase. As x increases, y is also increasing. But let's say when we plug in 10, we, instead of having a larger number than 38, what if we wind up getting like 35? And so what's happened is this. From here to here, the output values were increasing. But now, from here to here, the output values are decreasing, okay? And here's what that means. That means that somewhere between 38, sorry, well, really it's between 32 and 35. Somewhere in here, somewhere between 8 and 10, the output values, instead of going up, started going down. Now you may say, yeah, but they went up from 32 to 38. Yeah, it's possible that between 8 and 9, we might have gotten as high as 40 and then down to 38, okay? Now, don't get lost in the weeds. Don't worry about that. The only thing I want you to understand is that a critical x value is simply an x value where the output values, instead of going up, they start going down. Or instead of going down, they start going up. So basically, it's a change in direction for the function values, okay? And so that's what a critical x value is. And I'm going to show you very simply, it's a very easy little formula for identifying the critical x value in quadratic functions. Okay, so let's put a function up here. We're going to say f of x is equal to x squared minus 4x minus 21. This is a quadratic formula because the highest x power is 2, okay? Now, let's talk briefly about this lead coefficient and this critical x. The lead coefficient is very simple. The lead coefficient very simply is it's the coefficient of the x squared term. So like right here, here's the x squared term. The coefficient of x squared here, there's a 1 there. I mean, we usually don't write the 1, but there's a 1 there. So in this particular case, the lead coefficient is -1. It's very, very simple, very easy to identify. Now, what about the critical x? Okay, so let's talk about this for a second. Put this in your notes. To identify the critical x value, for a quadratic, now this is not the same thing for, we're going to see critical x values in other functions as well, but this formula is strictly for quadratic functions, okay? It's very simple. Your x, the critical, and there's only one critical x value, just one of them, okay? The critical x value is -b over 2a, where the b and the a are the same b and a from the quadratic formula. So recall, let's see where, oops, that's second, where f of x takes the form ax squared plus bx plus c. Now, in this form, I want you to notice that a is actually the lead coefficient. So we can actually answer lead coefficient as simply a equals. It's whatever the a is in the quadratic formula. Okay? Now, note also that the c here, that's the constant. Over here, the constant term is the c, right? And do you remember I told you that in polynomials, the constant term is also going to be the same as f of 0. But you know what? Let's get to that in just a few minutes. So we can see when we know what the a and the b and the c are for the quadratic formula, we are going to use the a and the b in this formula for the critical x value for a quadratic, okay? And so let's go ahead and go through these, identify each one of these qualities of this particular quadratic, okay? All right, so up here under critical x, I'm going to say x is equal to negative b over 2a. You may also note that this critical x value is actually a part of the quadratic formula. So look at the quadratic formula. We have negative b plus or minus the square root of b squared minus 4ac over 2a. If we were to split this up into two fractions with plus or minus, it would be negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. And so the 2a is the common denominator in the addition and subtraction. Well, look, right here, there's our critical value. So this critical x is actually an important part of the quadratic formula, okay? All right, so let's see what we got here. So in this case, let's identify our a, b, and c for this quadratic. So in this particular case, let's put them over here. A is equal to 1. That's our lead coefficient. B is equal to negative 4. And C is equal to negative 21. Okay? Whoops. Negative 21. All right? So now, the first thing we want to identify here is the critical x. And the critical x is going to be equal to negative b over 2a. So that's negative, and b is negative 4. So it's going to be negative 4 over 2 times 1. And so negative 4, that's 4, over 2 times 1, that's 2. And so the critical value is 2, okay? So up here, we're going to say, what's the critical value? It's x equals 2, okay? Now when we say, well, what is f of 0? Well, we already know how to do that. Remember, we said that to find the f of 0, we just plug 0 in for all of the x's, okay? So f of 0 is equal to 0 squared minus 4 times 0 minus 21. Well, 0 squared is 0. Minus 4 times 0 is 0. Minus 21. Well, 0 minus 0 is 0. Minus 21 is negative 21. So f of 0 is equal to negative 21. Note that negative 21 is also the constant term. Remember, we said that the constant term is whichever term does not have any kind of variable in it. And look, negative 21, no variable here. Therefore, the constant term is negative 21, which also happens to be c. That c is negative 21. And so the c for quadratics, the c is the constant term, and it is also going to be the value for f of 0. There, and that's not by mistake. It's always going to be that way, okay? All right, so now, before we look at a lot of this other stuff, we can hit the lead coefficient, which is always the a. The lead coefficient is 1, which is what the a is. So lead coefficient a equals 1, okay? Now, before we can do really much of anything else, we're going to have to identify the roots or the zeros. Now, we've already done this in the class. This is what we did when we solved quadratic equations, okay? And so we said that the roots are when y is equal to 0, when f of x is equal to 0. And so what we're going to do is we're going to put a 0 in for f of x, and then we're going to write out our expression, x squared minus 4x minus 21. So now what do we do? Okay, well, here's the point at which you just use any of the techniques, any of the methods that you learned when solving quadratic equations. So you can use the quadratic formula, you can use factoring, you can use extracting by square roots, you can use completing the square. Any one of those techniques is appropriate for doing this. Now in this particular case, I can tell you that this is factorable. The two numbers that multiply to negative 21 but add up to negative 4x are, add up to negative 4 are negative 7 and positive 3. So we're going to go x minus 7 times x plus 3. And now to solve for 0, we're going to set each one of these equal to 0. X minus 7 equals 0. X plus 3 equals 0. So over here we're going to have x is equal to 7. And over here we're going to have x is equal to negative 3. And so the two roots of this quadratic, or the two zeros, are x equals 7 and x equals negative 3. Okay? All right? Okay, so to create this sign chart, here's what I want to remind you. What we do is we draw a horizontal line, then we put negative infinity on one side, we put positive infinity on the other side, then we're going to put hash marks for each one of the roots. Now we have two roots instead of just one root like we did with linear. So what we're going to need to do is we're going to need two hash marks. So we'll put one here and one here. Now, we have to put them in order from smallest to largest. Now, negative 3 is smaller than 7, so we're going to put negative 3 here and positive 7 here. Okay? And so now what we have is, instead of two segments on the sign chart, we actually have three segments. We have this segment, we have this segment, and we have this segment. Okay? Now remember what we have to do. We have to take a number on the segment, not one of these numbers. It's got to be one that's like, for example, if we're choosing it from here, it has to be in between negative infinity and negative 3. The one for this segment has to be a number between negative 3 and 7, and the one over here has to be a number larger than 7. Okay? So over here, we need a number smaller than negative 3. Why don't we go with negative 4? Okay? So we're going to put negative 4 in for x in the expression. We're going to identify f of negative 4. Well, we're going to have to do negative 4 and then squared minus 4 times negative 4 minus 21. Okay? Well, negative 4 squared, negative 4 times negative 4, that's positive 16. Then we have minus 4 times negative 4, so that's minus 4 times negative 4, that's negative 16. And then minus 21. Well, 16 minus negative means plus, so 16 plus 16 is 32. 32 minus 21 is 11. And that is a positive number, and therefore all of the numbers on this sign chart, all of the numbers less than negative 3 are going to be positive outputs. Okay? Now when I say all the numbers, I mean for an x value smaller than negative 3, the y value is going to be positive. Okay? All right, let's do the same thing for in between negative 3 and 7. Well, let me show you a neat trick. Between negative 3 and 7 is 0. And if we were to plug in 0, we would have f of 0. Well, we already know f of 0. F of 0 is negative 21, and therefore all the numbers in between negative 3 and 7 are negative. Okay? So that's a neat trick. We can do that pretty much every time. Well, that's assuming 0 is in between these two numbers. What I mean is whichever interval 0 is on, we can use that number. Okay. Now, for this segment, larger than 7, we're going to have to plug a number larger than 7 in for x. So let's do 8. So we'll do f of 8. And so we're going to have 8 squared minus 4 times 8 minus 21. And so 8 squared, that's 64, minus 4 times 8, that's 32, and then minus 21. Well, 64 minus 32, that's 32. And 32 minus 21, that's 11. And that's what we got before. That's interesting. Wonder if that's meaningful. It is. So that's a positive number, so we're going to put that right here. And so here's our sign chart for this quadratic, is that all the output values, so the f of x values, the y values are positive for any x value less than -3. And then when we get to -3, y equals 0. Then y is negative all the way up to +7, where it equals 0. And then all the y values are positive. So we have positive values, then negative values, then positive values for y, okay? And so that must mean that if we went positive values, then negative values, but then they went positive again, that must mean at some point, so for a while, the values were getting smaller because they went from positive to negative, but then they went from negative to positive, which must mean that somewhere those output values turned around. They stopped going down and they started going up. And that's what we mean by the critical x. And notice this, the critical x is 2, and the critical x is between -3 and 7. Actually, it's more interesting than that. The critical x is actually halfway between -3 and 7. So our critical x value 2 is 5 larger than -3 and 5 smaller than 7. And that actually will happen every single time. Your critical x value will always be exactly halfway between your two roots, okay? And that's meaningful, okay? All right, but we'll erase that for now. We just want to keep the sign chart. We've already got the constant term. Let's talk about the rate of change. Okay, this is complicated. We can't do the rate of change because this is a college algebra class. And for a quadratic, the rate of change is actually variable. So there is a variable rate of change. It doesn't stay at one number. Remember with linear functions, we always had one number as the rate of change. Well, now we have what's called a variable rate of change, and we're going to say here we're going to say wait for calculus. You're going to learn how to do that in a calculus class, not in a college algebra class, okay? So you'll learn about the rate of change for a quadratic function in a calculus class, okay? So we're actually just going to, the only thing you're going to write for rate of change is you're just going to write variable, okay? It's a variable rate of change, and you're going to learn it in calculus, okay? So now we want to know intervals of increase, decrease, and constant. Okay, so let's talk about that for a second. Quadratic functions never have constant rate of change. They only have, or not rate of change, they never have constant intervals. They only have one interval of increase and one interval of decrease. Okay, and I'm going to show you how to get those right now. So for interval of increase and interval of decrease, okay? Oops. So the way we're going to, here's the deal with interval. One of the two numbers, because we're going to do an interval, right? So interval of increase means all of the numbers are getting larger. Interval of decrease, as the x values get larger. Interval of decrease is all of the y values are getting smaller as the x values are getting larger, okay? And here's the thing. This critical x value is always going to be included in the interval of increase and interval of decrease, okay? So we're going to put here, include the critical x, okay? And here's what I mean. Remember how I said that the critical x is where numbers either stop going down and start going up, or they stop going up and start going down. Well, that's the whole idea of interval of increase and decrease. So one of these numbers in here, well, one of these two is going to be the critical x value, and one of them here is going to be the critical x value, okay? And you might say, well, how in the world am I supposed to know which one? Well, here's what we can do. We can, basically put in a number that's next to 2. Okay? So let's plug in, let's do f of 1, and also do the other side of 2, let's do f of 3. So what we're going to do to be able to find the interval of increase and decrease is we're going to take our critical x value and we're going to go to a number larger than this and to a number smaller than this to see what happens, okay? And we're also going to want to know what f of 2 is, okay? So let's plug 1 in. If we plug 1 in here, we get 1 squared minus 4 times 1 minus 21. Well, 1 squared is 1 minus 4 times 1 is 4 minus 21, okay? Well, 1 minus 4, that's negative 3. Negative 3 minus 21, that's negative 24. So we know that f of 1 is equal to negative 24. Now, if you wanted to, you could actually use the remainder theorem for this. You could do synthetic division and use 1, negative 4, negative 21, and then put 1, 2, and 3 in the half box. But we won't do that right now, okay? But let's identify f of 2. So we're going to put 2 squared minus 4 times 2 minus 21. Well, 2 squared, that's 4, minus 4 times 2 is 8, minus 21. Whoops, minus 21. Well, 4 minus 8, that's negative 4. Negative 4 minus 21, that's negative 25. Well, look at this. This is interesting. Check this out. It looks like as we go from 1 to 2, as the x value increases, our y value goes from negative 4 to negative 25. That means that it's getting smaller, okay? So that's an interval of decrease. X goes up, y goes down. That's an interval of decrease, okay? And so we know that the interval of decrease is going to end at 2, okay? And that means it started at negative infinity. And so when we go to 3, we can be sure that this number is going to go up. We can be sure if we do 3 squared minus 4 times 3 minus 21. 3 squared is 9. 4 times 3 is 12 minus 21. 9 minus 12, that's negative 3. Negative 3 minus 21, that's negative 24. Okay, well this is negative 24, which is interesting because this was negative 24. There's a good reason for that, okay? We'll talk about it right now. So as x goes from 2 to 3, as x goes up, the y value goes from negative 25 up to negative 24. And therefore, that's an interval of increase. So our interval of increase must start at the critical value and then go up to infinity. And so we have now identified our interval of increase and our interval of decrease. Okay? All right? By using the critical value and finding out whether the numbers after it are going up or down or the numbers before it are going up or down. Okay? All right, almost done. Created the sign chart, got the intervals of increase, decrease. Okay, domain. This is an easy one. Just like linear functions, you can plug any number into a quadratic function and get an answer. There's no number that you cannot plug in here and get an actual defined answer, okay? So the domain of all quadratic functions is negative infinity to infinity, okay? Now, let's go ahead and do the limits as x approaches negative infinity and the limit as x approaches infinity. Well, remember, we used the sign chart last time. So let's go to where x is at negative infinity. Well, here's negative infinity, and what do we have right next to negative infinity is positive numbers, and therefore, that's going to be positive infinity. Now let's go to where x is approaching positive infinity. That's over here on the right-hand side. And again, we have positive numbers. Is that possible? Yes. In fact, with quadratics, the end behavior will always be both the same. Both the same. Both will be the same in a quadratic. Okay? So you will either have, for a quadratic function, your end behavior will either be both positive infinity or both negative infinity, okay? All right, so that leaves just the range. Okay, so how are we going to find the range in a quadratic? Well, the range is actually going to be related to the critical x value. And it's also going to be related to the interval of increase and the interval of decrease, okay? What we said previously is that the range is always going to be the between the minimum value of the output values and the maximum value of the output functions. Now, we said with linear functions there was no minimum because we always went to negative infinity on one side, and the maximum, we always went to positive infinity at some point or another, okay? And so what we're going to do to get the range is we're going to look up here at our limits, our end behavior, our limits as x approaches negative and positive infinity. And here's what I'm saying, okay? For the range, if both of these are positive infinity, then that means that there is no maximum, and what we'll do is, for range, if end behavior is both positive infinity, then the range is going to be a number up to infinity, okay? Because look, we know that the output values f of x goes up to positive infinity. So that means that there really is no maximum. So it's going to be some number positive plus positive infinity, okay? Similarly, if end behavior is the opposite, if end behavior, you want to put this in your notes, okay? If end behavior is both negative infinity, then your range is going to be negative infinity up to a number. The question is, how do we get this number? Okay, to get the number for the range, what you're going to do is you are going to plug in the critical x into f of x, okay? And so what you can write here is you can write f of negative b over 2a. You put the same thing here, f of negative b over 2a. That means that you're going to take your critical value and plug it in for f, which we actually already did when we identified, what were we identifying? When we were identifying the intervals of increase and decrease, right? We wanted to know from the critical x, as we go up to 3, is the number going up or is the number going down, okay? And so we want to do f of negative b over 2a, which is f of 2 in this case. Now, if you look back a few lines when we were doing interval of increase and decrease, we plugged 2 in and we got negative 25, okay? And now, since our end behavior are both positive, then we know that our range is going to go up to infinity, and its minimum point is going to be negative 25, okay? And so the range of this particular function is negative 25, comma, infinity. What that means is this is the limit, this is the range of all possible outputs from this function, okay? The lowest possible y value is negative 25. And so we can go up from there up to infinity. But what else that means is that you will never get a negative 26, you will never get a negative 27, you will never get a negative 100. It's not possible because the lowest possible value of this quadratic is negative 25. That's what range means. What is the lowest value? What is the highest value? Okay? Now, I know this was pretty crazy. So what we're going to do in the next video is we're going to do 3 more examples, but we're going to do them a little faster because we now have our notes, we now went through the process, and we know how to do everything.